look this. It's so we get we can combine the velocity, horizontal and vertical, in more equation for get the efficiency of the device. So next. Oops. Next. So we need some support. That's all. Thank you very much.
Okay, we have time also for a couple of questions. Anybody? Nope. Here in the front.
Thank you, Carlo. That was very interesting. Thank you. So you said that you had a prototype in the water. How long has it been? How long has it been out? 1 to 10 days. Okay. Something?
At the back.
Thank you.
Do you think? Do you think that your device could be used for predict different water like for floods or something like that, like a big wave coming or something like this, or for predict the weather?
I don't get your point. You mean that if we are prepared for different conditions of the sea with the device?
Yeah, if you can predict with
well,
the device.
we can test the behavior of the waves in the CFD simulation. So we can prove different situations in the simulation to be prepared for the worst.
Okay, thank you.
Okay, thank you very much. All right, our next speaker is Dr. David Romero from ENES, UNAM. Okay, perfecto.
Hello, I'm David Romero from the ENES Mérida, the neighbor. I represent methods for the evaluation of coastal vulnerability to hydroclimatic hazards, principally hurricanes. I will speak about two ongoing projects, one led by Dr. Luis Bojorquez from LANCIS, UNAM, National Lab of Sustainability, but where a lot of people of ENES is also involved, and people of Institute of Engineering of UNAM. And other project, which I lead on our team, with also people of the Center of Atmospheric Sciences of UNAM. The two projects integrated analysis of coupled socio-environmental systems, capacity development for coastal vulnerability assessment. The Dr. Luis will speak about it later. I will only present it shortly. And my project, evaluation of changes affecting extreme climatic events and the relation to the risks for exposed populations in the Yucatan Peninsula, Mexico. And it's a project that is just starting. The aims of the project: the first, investigate what analytical and technological tools are required to create theoretical, robust, and operationally viable procedures for designing adaptation policies that help to reach sustainable development goals. Based to take into account that vulnerability is a product of dynamic, complex, and reciprocal socio-environmental interactions on multiple temporal and spatial scales. The result will lead to a better understanding of the patterns of vulnerability that arise from feedback between public policies, coastal activities, and climate change, and the other generation of knowledge about the changes that have affected climate conditions and the evolution of the associated risk. The knowledge shall cover the extent of the phenomena, their frequency, spatial distribution, and the intrinsic and social parts of the evaluation of risk and its perception will also be determined. Well, the target problem. We are in a seminar of economic development, and a critical point for economic development is the risk management. An insurance company, FM Global, say every dollar spent in hurricane protection can prevent $105 in business property loss or disruption. It's a lot. So, economic loss because of hydroclimatic hazards may be critical in Yucatan coastal zone. We have seen it for Wilma, Isidore, or Hilbert. Also, risk is a product of threats and vulnerabilities. We can build knowledge on threats, but we can reduce the vulnerabilities. Here are the anticipated results from a project of Dr. Bojorquez. I will pass it very quickly. We are now in the moment of validation of GIS MCDA results. Very interesting things are done in this. Activities and deliverables identify the evolution of a risk relative to hurricanes principally, spatio-temporal variation of the frequency, and the amplitude of the phenomena. Well, I think the problem is going into to England with this year Lorenzo, Pablo, which were very strange hurricanes, and we are noting problems in the North Atlantic and the climatic response to, we don't know what to sea surface temperature or something like that. Also, novel analysis aimed to generate scientific information for decision making and computational tools that facilitate citizen participation in the formulation of public policies and for sustainable development. Well, I'm sorry, I'm maybe the only geographer here and I don't show any map. It's a shame. Resources, well, most of the data we are using are from NOAA, INEGI, and Yucatan State. The projects are funded principally by UNAM, but our projectors named PAPIT, 2-3 years UNAM funding, and Obviously, successful project updated can have a new grant, and of course, other support needed. Well, trying to analyze and do a correct modeling of the relations between North Atlantic sea surface temperature, sea currents, and hurricanes. And that's all. Thank you, because it's time to go to it.
Any questions for the speaker?
Thanks for the overview. It's a very interesting project you have. What sort of links have you identified with climate indices such as Atlantic meridional oscillations, which are SST anomalies essentially?
I'm just starting to work about it. I'm seeing, well, using Fourier and his friends, some variation in sea surface temperature, and the problem is that the hurricanes are not so continuous than sea surface temperature, and it's very difficult to make the identification of the causes directly. We have seen that there is a movement of the 26.5 degree temperature zone in the North Atlantic to the north, but also a lateral movement which seems to be periodic. But there are some things very interesting, but we are just starting on this. Lena.
All right, since we have to meet our schedule and we took twice the time in the last break the time that we were supposed to take, we're going to continue with our second keynote speaker of the day, with Dr. Gabi. And finally, we are closing this evening with two more talks after the keynote conference. So, Gabi? Matt? All right, Matt goes first.
Hello, sorry, that was the first I knew of that change as well. So, sorry, I was in a bit of a rush earlier on, so I forgot to thank you all for, thank the organisers for the invite to come. It's my first time in Mexico, and I'm very much enjoying myself so far. Thank you. So I want to just expand on some of and do a very focused talk really on one of the applications that we've been using our marine autonomous systems for. This is a project that I lead in the UK called AlterEco, which is an acronym that stands for an alternative framework for us to assess marine ecosystem functioning in shelf seas. So I think that hopefully is going to be quite relevant to some of the things that are going on here currently. I won't go into the details, but it's quite a large program, and there's a need there, therefore, to split this up into its different components from the physical oceanography, biogeochemical. We have a specific interest in oxygen deficiency. I know that's something that's also transferable through to the Gulf of Mexico and surrounding regions. And then there's a very large program at the end of that in how we synthesize this information and deliver it to our stakeholders. So this program is actually not just, is quite unusual for a UK-funded project. It's funded by our Research Council, NERC, but also directly funded by the Department of Environment, DEFRA, and WWF, who also provided some funding. The reasoning behind this, the motivation for this work, is very much around how we currently, you can't read this writing here, but this is an assessment framework for how we assess the environmental status of UK marine waters. Because the UK is part of the EU system, we have certain statutory requirements each year to monitor large parts of our system to provide an assessment of ecosystem health. And that's very complicated. A lot of these indicators, if you could read them, would say things like shellfish, cetaceans, seabirds, and these monitoring and understanding everything through from the base of the food chain, even through from the physics through to the food chain, and actually how that impacts on those species. It's very difficult, very expensive, and also not necessarily particularly effective in that you're typically constrained to just a few case studies. So the key here was to try and improve the capability there through the use of autonomous vehicles, such as these that I've already talked about. One of the other developments that I've not had time to introduce, but I know is relevant to quite a bit of the work done in this region, is also the development of new lab-on-chip sensors. So we particularly at NOC developed these nutrient sensors, which is a microfluidic system, the same as a nutrient analyzer that might be on a ship, which is sort of this size and requires a PhD-educated chemical engineer to run. And we've automated this into something that is you can hold in your hand and can also then be placed inside one of these gliders. And this project was the first to accomplish that long term. We also we have a range of other vehicles. The area of interest is, if you're familiar with the UK and Europe, so it's this North Sea, very large area here. It's actually the most studied piece of marine water on Earth. People have been trying to work out why all the fish are disappearing from there for at least 300 or 400 years. And it's quite an interesting system in that the Atlantic streams in and essentially has this northern circulation cell where water comes in but quickly comes out through the Norwegian Trench. Internally, however, things are quite quiet. Relatively low tidal velocities, low circulation, and therefore we get these oxygen minimum zones forming in the middle there, which is quite detrimental. So we focused our study on an area in the middle of this sea, using a whole range of different vehicles, and this is just a timeline here showing that we managed to have 2 vehicles in the water continually, at least 2, through eventually what was an 18-month period. So this is a case of putting one vehicle in after the other one. The nice thing with the gliders, I know I'm going to be constrained for time. I did have a deployment video, but I'm going to leave it to try and have a bit more explanation. But the nice thing about these type of vehicles is that we can deploy them near the coast in a small vessel. It can make its own way out to the survey area, maybe 150 miles offshore, undertake its survey, and then we'll replace that. And as it's coming back in, we can do the recovery. And that's a very cheap and effective method. And this is just an example, one example, transect. Here going from the north, coming onto this bank system. So the gliders maintaining lots of up-down yo-yos, which are equivalent to a ship CTD profile. This is just showing temperature here. And you can see the strong horizontal variability in that bottom mixed layer there, which is also replicated in the oxygen content of that water. We see this front development around the bank, and then this is actually coming back off the bank, back through this system as we do this repeat. We managed through that program with this one type of vehicle, we used 2 types of glider, to have over 50,000 profiles. So those of you who've worked at sea, you've managed, if you've gone and made a profile from a CTD or a handheld winch, then you'll realize the amount of effort that we're saving or being able to expand on there is enormous. A second type of vehicle, again a glider, but achieves another 15,000 profiles. This time, instead of looking at the behavior over the bank, was actually covering a MPA, a marine protected area, further to the north. So again, another extensive time series. And this is what that data starts to look like over a long period of time. This is a 1 year slice out of an 18-month time series. Those of you familiar with our system will realize that rather than have a sort of permanently stratified system, we go through a winter period of mixing through to a spring stratification and then summer stratified period, which then eventually gets broken down by winter winds. And so you can easily pick out the lovely physical mechanisms that are driving that system. We're then also able to clarify the chlorophyll, so you can see this is the spring bloom period here. So we get as this water stratifies, the well-mixed nutrients interact with the increasing light during spring. We get a spring bloom, and then that provides a deep or a subsurface chlorophyll maximum through the summer. Again, a really nice signal. And this is the response in our oxygen. Those of you who have particularly keen eye will recognize some noise in that system. So we're still struggling with things like biofouling. That's a major issue for us for long-term deployments. But then we get this very low-level oxygen that's problematic to us in our shelf system. As I said, we've been using also these novel nutrient sensors. We actually had almost 12 months, 10 months data, sorry, of a winter, summer, through to next winter period of actually measuring in direct in situ measurement of nitrate plus nitrite through that full system on an autonomous vehicle. So that's certainly the first time that's been done. We also managed to trial a phosphate sensor, and I've currently got a silicate sensor out on a mooring, so now we're getting to the point where we can actually do the full macronutrient budget on autonomous systems. So it's a very exciting development. And I've almost finished the last two slides now, but the other development that we've managed within this is putting fisheries acoustics in the base of one of these surface vehicles. This is a dual frequency broadband fisheries acoustics that have been deployed on the back of what we call a wave glider, and this is able to be steered up and down, back and forth on the same transects following the gliders. And I apologize about the colors here, but what this is allowing us to do with the dual band frequencies is pick out different fluid and gas-filled zooplankton in this case, and also occasionally pick out fish signatures. And what we've identified here is how the feeding cycle changes relative to the spring and then summer conditions. There's a lot of information there. Again, please do come and see me if you're interested. So a bit of a summary, but I think this is a key. This type of experiment is a real step change now. We're moving past the sort of single deployment or deployment of a few of these platforms, using some of the technologies I showed in my earlier talk, where we're able to then combine multiple deployments of multiple vehicles into a single interface, a single piloting tool, if you like. We're then able to deploy at relatively low cost these very large continuous deployments in our Chelsea environment. So hopefully you can see the benefit to that. And I do feel that certainly just from seeing the talks I've seen this morning, there's certainly a lot of overlap here with what I've been seeing is local interest in terms of scientific research. And if I do have time, I don't know how much time I'm stealing, but our next steps, the WWF interest here was to try and be able to take these type of technologies outside of a rich nation like the UK and see how transferable that was, in this case, into East Africa. So this is some work that myself and Gabby have been involved with in Tanzania. We have just finished this deployment, but if that works, the idea here being that we can take these same levels of technologies and put them into extreme environments, in this case in East Africa, using a combined, sort of an integrated approach, using the model data to feed information into how we should manage the gliders. And I'm pleased to say, well, this is a simulation. We successfully achieved that this summer as well, but there's plenty more information about it. That's me finished. Thank you. Should we do a quick change? Okay. There's no chair, so I thought I'd take questions.
Does anybody has a question? No?
Behind you.
Excuse me, Matt, I'm not specialized in marine terms, but what is exactly the acoustic waves are related with what in talking about marine studies?
So do you mean the acoustics slides that I showed? So there we were using fisheries acoustics. So it's acoustics that are tuned to reflect off small zooplankton, particularly, and small fish. So they're allowing us then to identify the movement of those fish, identify biomass. So now we can do fish stock assessments. And also the key thing there is looking at the zooplankton. We're able to investigate the zooplankton behavior through the different seasons. So the key there is to try and take the measurements all the way through from the physics, through the chemistry, and all the way through into the fish, but using this fairly small fleet of autonomous vehicles. I can talk with you more about it.
Thank you very much.
Hi. Following on the question, interesting question on acoustics. I know that there's a lot of development on sensors for biodiversity, especially megafauna. And have you tried to put some of this acoustic, I don't know, cetacean monitoring? I mean, those gliders spend a lot of time in the sea, and you know where they are.
We do a lot of passive acoustic monitoring. A lot of that work is actually funded by defence because they're very keen to identify cetaceans, particularly when they're doing seismic activity. It never looks good if you're killing lots of dolphins, so the military like this as well. But that allows us to do quite a lot of scientific research off the back of that as well. It's a very tricky field, though. If you've got a low-powered, if you want to do acoustic properly, you need lots of power. So we have to start being a little bit clever about the types of sensors we employ. But there are a number of things that we're working with, and we're currently putting a new proposal together actually in that space. So happy to talk more. Sorry.
Okay, yeah. You mentioned that you can use the glider, coastal glider. How shallow can be, and how is the response if they found a change in the bathymetry? How quick can react?
Sorry, what was the first part of the question?
The first one is how shallow is, and the second one is how quick can change.
So this particular mission, the reason we were running two different types of glider in different spaces, one of them only works in deeper water. So that one had to have at least 100 meters. The second type of glider, the Slocum Coastal, was okay down to about 30 meters. We have used them down to 15, 17 meters. They get a bit scary. It gets quite exciting, I think is a good way to say that. I think realistically, though, we're looking at developing new equipment. So one of the other developments that I very briefly showed earlier this morning was the development of small subs, literally this big, 4 kilos. They don't have a long duration, maybe 2 days. I was talking to Alex about this as a potential option for the future, but you could potentially put them out on your boat. They can just hold the same depth, so you can use them in 1 meter water if you want to. Also, they can be used to undulate. So I think new technology is needed to get into the very shallow water. And the other thing was, how do they respond, I think, to rapidly changing topography? Well, they have an altimeter, so there's an acoustic pinger. The coastal gliders can turn within about a meter, so if it sees it, it'll turn. Some of the other vehicles are a little slower. Once you start going into faster vehicles, the bigger vehicles, now you've got momentum, and that becomes a problem. And they're a lot more expensive. But yeah, 1 meter capability is typical. My engineers, though, like to have 5 to 6 meters, and I'm always trying to push them really close to the bed.
The nutrient instrument you showed is quite impressive, and it's chemical.
Yes, it is. It is no different than the chemical nutrient autoanalyzer you have on a ship, but it uses a single channel.
And does it work okay? I mean, obviously you have tried it with compared with measurements, like from a ship or from a
absolutely
boat.
In fact, when I say it does a single channel, it actually has 2 channels. So we also run a without getting too technical with the rest of the audience maybe, but we actually run a blank and a standard at the same time. Okay. So every sample actually has a standard and a blank. So we run 3 different channels at any one time. And then the real difficulty in that is getting the system flushed through, make sure you're taking a clean sample. The really usefulness of having this long period deployment was that while we thought we had already fixed all these problems, when you start trying to do it for 3 months at a time, every 3 months, we actually started finding all sorts of different issues. So I'm pleased to say for nitrate, nitrite, we're happy, that's ready to go. Phosphate, I think because we've already learned the lessons from nitrate, will be a much quicker process. We have the first now in silicate, we've been using successfully in Greenland on moorings for some time. Yeah, it's really exciting development.
Thank you. It's a very nice piece of instrument. Thank you.
It's me again. So what we're trying to do now is as you show us your projects, we are just trying to quickly show you some of ours that you may be interested on. So that was Matt with robotics and observational oceanography. So now it's me representing the modeling group. So interesting modeling applications that we've been delivering in various places, particularly close around the Yucatan Peninsula. So I'm going to show you 3 different projects if there is time. So the first one, it's the project in Belize, which was done through the Commonwealth Marine Economics Program. the modeling part of it was to develop a high-resolution regional ocean circulation model for the Belize coast and its applications, but it's a massive multidisciplinary project that involves most of the groups at NOC. So I'm going to outsource here and play an introduction by Richard Sanders, who is the OEB group head. So it's just YouTube, if we can play the video. Maybe. Hopefully you can hear him. There we go.
Over the last year, scientists from the National Oceanography Centre have been working with local partners in Belize to understand and steward the natural marine resources. Belize is home to the world's second largest coral reef system, which is a biodiversity hotspot and provides employment opportunities to local people in sectors such as fisheries and tourism. Belize is also the most forested country in Central America, with its ecologically diverse rainforest providing important habitat for many species of birds and animals. However, we're observing a transition to a more agricultural system, with species such as palm oil, banana, sugarcane and other cash crops becoming increasingly important in the local economy. As this transition occurs and forests are replaced by agricultural systems, we begin to see changes in the quality of the water that drains these systems. Soils and nutrients are leached from the landscape into the rivers, with consequences for the ecological health of the rivers and coastal seas.
The Macal River is influenced by 3 dams, which is changing the flow of the river. In fact, also changes in colors. The Macal River is coming all the way from Guatemala, have different impacts, in particular from agricultural development, effluents released from households, and so forth. So we are interested in finding the quality of the water, because as you see, you can see a complete separation of the color of the water. One that is more brownish and lighter, one that is more greenish. So we want to see, what we are picking up in terms of the quality of the water.
To better understand the consequence of these management changes on the coastal ocean, rivers and estuaries, we undertook a sampling program working in Belize. We sampled in the main river and in different subcatchments draining different sorts of landscapes like forests and agricultural systems. We sample for a range of water quality parameters that allow us to link the usage of the land through to the water quality and ultimately to impacts on human systems. We can then track the river plume out into the coastal waters, where it begins to impact on the economically and ecologically diverse and valuable coral reef system found just offshore. These data and information allow informed choices about the management of the river, coastal and reef system to be made in a holistic sense alongside the agricultural systems on the mainland. Rivers are highly dynamic systems, which means they change rapidly. This dynamism means that we need to measure them frequently, so we've been establishing monitoring programs with students from the University of Belize to make frequent measurements so the impact of flash flood events, for example, can be understood. This latter part of the programme has demanded that we build a collaborative relationship between the National Oceanography Centre, the Centre for Ecology and Hydrology and the University of Belize in Belmopan. This three-way relationship is becoming increasingly productive and has led to some amazing insights into the coastal rivers and how they're coupled to the ocean and to the landscape. So one tool we've been using in the coastal waters of Belize is an autonomous surface vehicle known as the Sea Worker. This allows us to access environments that you couldn't access with humans and is a low-cost, sustainable solution to monitoring the marine environment in a diverse set of ecosystems around the world. We use these camera systems to make detailed maps of the coral system and relate that to the distance away from the river. By monitoring the ecosystem health at the sea floor and the water quality in the river, we can create a detailed picture of how the two are linked together. We've also been focusing on another important component of the offshore system, seagrass meadows. So seagrass meadows are shallow marine plants that live between mangroves and the coastal ocean. They're important carbon reservoirs. Their powerful root systems burrow deep into the subsurface sand, and as they fix carbon from the atmosphere, they also sequester carbon coming down the rivers and out of the mangrove swamps. So seagrass meadows can become important carbon sinks with a big role to play in fighting climate change, coastal carbon budgeting and national carbon budgets. We refer to the carbon that seagrass meadows, mangrove swamps and salt marshes store as blue carbon. It's relatively understudied, and a holistic programme looking at the controls over this, along with the processes that are producing it, is quite unique in the world. Belize is leading the way in sponsoring these sustainable efforts to understand its blue carbon reservoirs. Ultimately, we hope to be able to value these things in order to steward them further going forward. So we undertook a programme of work with colleagues from the Continental Sustainability Association to work on the blue carbon environment of the reef system, looking at the amount of carbon stored, flying drones around over the surface to examine it from altitude, and ultimately using satellites to integrate across the whole atoll system to get the big picture of how much carbon is stored in Belize's blue carbon ecosystems.
So that's the big introduction to the holistic project, and I'm just going to talk to you about modeling-wise what we did. I don't know how to play it. Can you play the animation? So why do we need ocean models? So the ocean is highly dynamic as opposed to land systems. So you can have a habitat that is there today and it's moved hundreds of kilometers away tomorrow. So we need to know basically the ocean currents drive the whole ecosystem and it's not fixed in time nor space. So with ocean models, you can get this variability, or at least a very good representation of it. So this is the global NEMO, and as we say, as Laura mentioned, these models do not represent the coastal processes. So what we do is with this relocatable NEMO tool, we do high-resolution coastal models for specific places of interest. So this is our relocatable patches. So all these smaller models have been developed for specific projects in different parts of the world. So Jeff already talked about the big one, but then we did one specific for the Mesoamerican barrier reef for this Belize project. As you can see, it covers part of the Caribbean coast of Yucatan, Cozumel Island there. So these are the details, maybe no time for all of it now, but it's 1 kilometer resolution. So maybe it's more useful than some of the models that have been shown, like HICOM or others. So it includes river forcing, at least for the Belize area, we focus on them. So these rivers, we tailor them from global databases based on real measurements that they have of the outflow. So we ended up modulating even the rivers that we don't have real data. We at least added this seasonal variability. This is months, this is flow, meters cubed per second. So for some of them in the global database, you have a number. That's the annual mean. And we originally ran this model for 20 years, and then we realized that it wasn't realistic because of the rivers. So we took these seasonal modulations from observations from the river we know, and we adjusted and applied it to all the rivers we are including. So if you see, this is the actual model running, but this is temperature and the color and surface velocities. So it's more evident. Well, it's evolved over time. As I say, we have 20 years of these. It goes from 1995 to 2015. But in the salinity, you can, this is just 1 year in this animation, it's 2015, going every day. In the salinity, you should be able to see more of the blue is low salinity, so that's where all rivers outflows are. It includes the Chetumal Bay. How realistic it is, I need you guys' observations to tell me. But this is it, the starting point. We have data, and for the people participating in the ocean modeling workshop this afternoon and tomorrow afternoon, we're going to be playing with this model. And we did a cutoff, as Richard Sander explained you. A lot of the interest is capacity building, so we don't want to do this and leave. We want you to guys to keep the capability of doing this in the future. So capability development, that's how we started with this workshop, and we did a tiny model just for Belize City, so that's what we will be playing also in the workshop. So we will give you all the data, so you, as Jeff mentioned, we containerize also our models. So you can actually run Nemo in any system, in Windows and Mac, with this Docker container in your laptop. This is very small. I usually run my models on the UK supercomputer with 3,000 nodes or so, but this one you can run in any laptop. So we, of course, we do validation with observations. There's very few of them. I'm not going to go into the details of that. This is basically our workshop promo. So this is what we will be doing, building and running the model and doing some basic diagnostics. We're using Python here. A lot of us are still in the MATLAB Python transition. And then tomorrow we're going to do the application of particle tracking. As you may have catch, the applications that they were interested on originally, well, it's ocean acidification impact on the reef. We didn't went as far as to model that. This is on the following steps to do, adding waves and then basic biogeochemistry, so we can model ocean acidification. But we didn't go all the way there. We had a year or so for the modeling component. So this is the little cutout around Belize City. And so the application they were interested in was the relationship between the river outflows, land change, and how this impact the reef. So tracking the river plume is one of the things we can do with the model. This is just the salinity, low salinity signature, but we can do it with Lagrangian particles, or we can do it with a really passive tracer similar to salinity. So then the other thing they turned out to be very interested was sargassum tracking and arrivals. So this is my work. This is what I like to do, particle tracking, individual-based modeling. If you can run the animation, guys. This is just a particle looping around with the tides. I don't know how. So there it goes. The thing is that imagine a coral spawning. So you have millions of particles, and each of them it's maybe going different way, even if it started in the same coral head. So I'm just trying to simulate this. I will never have as many particles as eggs a coral can release or a fish can release. But so it's all statistical. It's all statistical. So for the sargassum tracking, for Belize, it's very idealistic at this point. I'm just sitting in the offshore boundary of my little model, and then I track where things go. And I'm doing releases every month for the 20 years. Although sargassum really started to be a problem, I think, in 2011 onwards. So it's very idealistic at this point. So I actually call it just offshore stuff. It can be plastic, it can be debris, it's just passive particles. And because of the uniform seeding, this doesn't have to correlate with reality. So then for the analysis, I partitioned the Belize coast, the mainland coast, into these 62 boxes, and I see each different month of this conglomerate of the 20 years, the arrival. And you're supposed to get, according to this very idealized model, south of Belize City is where you get the most stuff coming from offshore. And you start to see it around April. And then April, May is where you see it. So whether this correlates to reality. But it's a starting point. So we can refine from there. I think the easier way to refine this, or the first thing to do, is to, instead of uniformly seeding, we can seed from satellite imagery. There is products that are specific to sargassum. So we can see where the sargassum patches are offshore, and then from there we seed and we track, so we know where is it going to come into shore. This is ideas that after a workshop, the modeling workshop with them, we concluded these are things we could continue our collaboration into the future. So then, because some people here are interested about oil and gas. This was my first project at NOC. It's called Anchor. So all of these dots is oil platforms in the North Sea. The ones with triangles is where there is biological information. So the industry actually knows what's on the platforms, what creatures are growing in there, because they survey with ROVs. But they don't release this information to scientists often. But in this partnership, they did. So on the triangles, we know which creatures are there. And my biology is very rusty, but I think it's, no, what are these creatures? A mussel, well, in these 5, there is a soft coral, a hard coral, a barnacle, and a dead man's finger. That's the common name. It's a sponge. So different creatures, and I characterize them in my model as virtual larvae having different behaviors. So this is an industry partnership then with science departments in the UK. These were the main goals of the project. So basically, whether this is an interconnected network, the platforms themselves, and whether they connect to natural habitat. And then is there variability and the connectivity for the different species, and what will be the effect of decommissioning these platforms, so basically removing them completely. Nowadays, because most of them have been in the water for more than 10 years, some of them are really old, like 70 years in the water, they are part of the ecosystem now. So this is how they look in the surface, but the legs are covered by this cold coral, Lophilia, which is endangered in the natural population. And they actually attract a lot of important, even fisheries important species. So they are acting like artificial reefs. But do they have an ecological importance? That depends whether they are connected among themselves and connecting to the natural populations. That for Lophilia is up here in Norway. There's actually some marine protected areas, and we find that they are. It's a highly interconnected network, and they actually providing propagos to marine protected areas near the fjords of Norway. So this is how I characterize my virtual larvae. These are the things I can vary for them, so they are not all equal, and they are not just passive particles. So basically, the spawning season, this is something that biologists tend to know when their creatures are releasing eggs. So the depth range, this is for the adults. This is from the ROV surveys of the oil and gas industries. They know where the population is established. So the cold coral, it likes to be deep. And this is basically the depth range of the adult population. And then the competency period, the pre-competency period is that they will drift into the water for this period, and they are not ready to settle. So if they found another structure, they will not connect because the larvae is not developed enough and they're not ready to settle. And this is the total larval duration, so including this competency period, that is this period when larvae are seeking for habitat to settle. And the main thing is behavior, so they are not passive anymore. So in here is limited what I can model. I cannot model horizontal swimming, and so it's mainly on the vertical behaviors. So people know, for some species, some biologists know from surveys at which depth the different stages of the larvae live. So I can do this variation. For example, for the cold coral, so the early larvae, they remain in the upper 20 meters, and then they migrate with some vertical swimming, which I can model. And then when they are late larvae, they are bottom-oriented. So they go deep looking for habitat because this will be their adult depth range. So this little creature, it was just neutrally buoyant. So this is passive in the middle of the water, just released at this depth. These guys like to be near the surface when they are early larvae, and then they migrate in the vertical, and at the end they also sink. So it's just these periods and this vertical orientation and vertical swimming speed that I use to differentiate them. This horizontal swimming capability is just a random walk, an added random walk on the horizontal. Real swimming is really, really hard. So then these are some of the results. Because we only have biological information for very few platforms, we extrapolated this depth from this depth range. So we say if a platform has this depth, it's likely to have this creature. And with that assumption, we see that in all platforms that are basically good habitat for the different species. So Solophilia, they like to be deep. They are only in the northern North Sea. And this, what you see, the color, is the actual trajectories. So it's what we call an spaghetti plot, but basically it's the footprint of the tracks of all the particles that are released, where they will go during the whole larval period. So you can see for some of them, they are all connected. This one is the bottom-oriented larvae. So if you're in the bottom, you move less and you connect less. And then we did this gridded because that's obviously very messy. And then we can see measures of connectivity. So this is some sort of cluster analysis. So if you have different colors, that's you're strongly connected within the same color, but you're still connected to everything else with color. So this is the number of clusters. So we classify the different species as for the most connected and the least one. And that seems to be correlated, the number of clusters you have with the larval duration. And that's that. And my last one, if there is time, this is old work from my PhD, but it may be very interesting for you because it's connectivity on the Mesoamerican barrier reef that you have offshore of Cancun, Isla Mujeres, Cozumel. And as Laura mentioned, it's a very large barrier reef, so it connects Belize, Guatemala, and Honduras. So I had a partner site in Africa, but I'm not going to talk to you about that one. Just so you know, there is a similar ecosystem in the other side of the world, in the shores of Kenya and Tanzania. Basically, a northward predominant current, offshore reefs and islands. So this is Zanzibar and Pemba, which Matthew showed a video of. So this is what I was doing, 2 sites, 2 different species, but it was a coral, so a passive, very short larval duration, and then a fish, which various levels of complexity. So also passive, so the difference with the coral is just the larval duration that is very long, a month or so. I was trying to do this Acanthurus genius, which is the surgeonfish. And then the development of larvae is directly related to the temperature of water. So this being an individual-based model, I can consider the temperature that each larvae experience, and based on that, develop them faster or slower. So each of my particles is now different. I have a population with variability, hopefully representative of a natural population. And then behavior, I added this ontogenetical vertical migration. So it's, as I was telling you for the previous project, they migrate during their larval life at different depths. So this is just numbers of how I characterize them. An important thing was this perception distance. So how do I make a coral different from a fish? So a fish can swim a lot. So I just assume if it finds a reef within 40 kilometers radius, this is a very strong swimmer, and the late larvae of it can swim for 72 hours straight. So it will very likely be able to swim 4 kilometers. And they perceive reefs through sensorial cues, so sound, chemical cues. So they know they are there and they can reach them. So that's a very important thing that differentiate them. And basically, just the analysis, I ended up with, I seeded every reef in the Mesoamerican barrier reef independently. So it was huge and messy if I just partitioned by latitude. So then I did these little areas. So North Mexico 1, North Mexico 2, Cozumel, West, East, blah, blah, blah. And the atolls, Chinchorro Bank, Turnafe, Belize. And then I did the analysis for that, so it's easier to interpret. So this is a classic connectivity matrix. You cannot see anything, I know, but trust me. So this is just basically the source where I release them, and this is the end places where they connect. So if you see a dot, you can say that, for example, North Mexico, which will be here, it's connecting to every place that has a dot. And then you can add the variability of temperature, which can be a climate model indicator. So we know the water will be warmer, we know how much. So what I did is basically just take actual years that already passed, 2005 and 2005. So they had for other reasons. One was warm and one was cold. But I can see the variability that that creates on the larval duration and on the connectivity. And I can extrapolate that to climate change interpretation. And the last thing, it has an application for marine protected areas, because you can identify reefs that are good sources. So basically the larvae that comes from them goes to many different places. So preserving this reef will be probably a great investment. And you can also have, so this is a source and sink maps, we call them. So a sink, a place that with a red color here, it means it's receiving larvae from 600 other reefs. So you may expect a lot of genetical variability in there that you may want to preserve, because that gives you resilient to climate change, to any stressors, anthropogenic or natural. So you can evaluate if you have a marine protected area, where is it having impact? Is it the best place for you to invest on protecting this site as opposed to any other? So it's basically a tool for management. And that's it. I was going to run away, but if you have questions, I stay.
Hi, just a comment. There's tell Richard that Mexico is doing a lot of work on blue carbon, so it's not just Belize that it's impinging on the fringes of success and whatever. It's a lot of work here. But the main point is, like, in your Sargassum model particle tracking, are you including windage into it? Can you include it easily? We have seen from the data and the tracking that it follows windage a lot, and we have also found something which might interest Jeff, that it looks like it traps into kind of large Langmuir circulations.
So we are looking on ways to continue this project, and what we are thinking is the next step is to include stock drifts from waves, and this is what we have considered. I also think we need a very high temporal resolution atmospheric, so because the sea breeze, it starts to have a very important influence very inshore in the reef lagoons. Basically, I wouldn't trust my model past the reef, so we need to do things to include those physical processes. So that's why we are here, and that's why we're collaborating with Belize. And just that's what we know from the Americas. So we know our Belize partner, and we were the first working in blue carbon in Belize. Any other questions? Everyone is ready for lunch. Me too. Laura.
Maybe we can try to figure out how we can. We are going to do some experiment, and I think I told you already. Then next year we start to build these buoys. We can try to do some experiments. You can test your numerical approach, and that will be great.
Same. I am very excited about your results and your developments of these devices.
Okay, we're our two last speaker. The first one is from Enes UNAM, Applied Mathematics and Computational Modeling Department. Who is our speaker? Ismael. All right.
¿Perdón? Ah, sí. Ok. Okay, me again. I'm presenting now the Department of Applied Mathematics and Computational Modeling on the ENES Merida, which we are actually, as I say again, your neighbors on the site. So we're just starting today with the lecture, so we're quite excited about that. And so it gives you like an overview of the stuff that we are doing in this department, so we can interact a lot, and with NOC as well, obviously. It could be a longer, more detailed, more details on what we do. So I was prepared for 20 minutes, but I think I'll just brush over. So the aims of the department is basically to gain substantial knowledge on the Earth's physical phenomena and all the processes that are interlinked with global, regional, and local scale. So the stuff that we've been talking about all this morning is basically all this. But we also like to apply and develop monitoring and computational tools to alleviate regional and socioeconomical changes. So we want to apply knowledge as well, and not only for governments, but also for businesses. And the scopes are, we go from the fundamental oceanographic, continental and atmospheric physical processes, the applied on energy, as I mentioned to you before, water quality and pollutants, coastal erosion and restoration, and structural design, and coastal zone management, some of the areas that we are interested in. And the techniques, well, they come from the oceanographic and hydrological surveying with the oceanographic instruments to high-performance computing and computational fluid dynamics, and also remote sensing and experimental designs on the development even of some instrumentation as well. So this is the fields of research of our interests. It's come from physical, ecological, and morphological feedbacks in coastal environments, underground water flows, submarine groundwater discharges, and salt intrusion, potential for renewable energies with salinity gradients, which is quite a novel approach for energy, currents, as I mentioned to you before, tides, waves, vortex-induced vibrations, hydrodynamics in coastal areas, etc. So I'll carry on. This is not a presentation, but I'll carry on anyway. So we use the high performance computing for the energy generation. For example, this is an element which will be being acted upon by the fluid and will be generating vortexes and vibrations, and these vibrations are used to generate energy. So, and this is all made in a high performance computing techniques. Okay, this is another detail of this element. This is the elements of fluid that will be coming out of this oscillation, and this will be generating energy with the movement of the element. Okay, another topic that we are very interested in is in the use of ecosystems for coastal protection. And in this case, what you're looking at here is a dam break, simulating a tsunami over elements that can bend, which will be basically trees. So the use of trees or woodlands, could be mangroves or palm trees, to protect the coast from a tsunami in this case, but it could be from any other wave or hydrometeorological event. This is the details of this model that have been used for that. Okay, this is, how can I do With laboratory measurements also, we are interested on the movement of sediments close to the bed, and numerical modeling of that as well. So we can study to the detail the erosion at the coast and the possible solutions for that. This is another scheme of this numerical model. So you can see the waves on the swash zone coming up and down the beach. Okay. This is some of the work that we've been doing in order to assess the effects of waves and currents on beach morphodynamics and studying inundation. This is in Holbox. So we can help the governments to decide where to put the developments in order to avoid future problems of erosion using these tools. This is sea level in here, and what you're looking at here is the wave heights for a given. This is 3 meters. It was an instrument installed in front of Holbox, and this is a numerical model where you have the beach profile and the waves approaching. This is another overview of that, giving us the erosion at the coast. Okay, and this is used for vulnerability assessment on different profiles that were measured in the field, and to see where this inundation will be worst, putting areas that are not good for development, basically. Okay, we also do several work on hydrodynamics of coastal lagoons using instruments to measure the bottom, the bathymetry, and also in different vehicles, it could be manned or unmanned vehicles, to measure ADCP, CTD, and all these variables that we have been talking about this morning, which are fairly useful. This is about the upwelling that I have told you about in the morning already. It's a very important process that we want to understand much better using measurements and remote sensing, and as Alex mentioned to you, numerical modeling as well. Okay, we also been involved in doing coastal and continental shelf hydrodynamics modeling. This is a numerical model using Delft 3D, in which we study the dispersion of red tides. So we see the phytoplankton position in time 1, and then we use this numerical model to run the simulations, and this will be the initial condition, as I mentioned, where the phytoplankton was seen, and after running the model, we can know with a fairly good, we can know fairly well where it could end. And a red tide is anomalous growth of phytoplankton on the coast, and this anomalous growth can be fairly bad for fish because it can basically kill fish. And when this event occurs, you're not advised to consume any goods from the ocean because it could be harmful for your health. So the government is very interested in this type of developments where a red tide event comes out. Then they need to know if it's going to approach to the coast or not, and when. So using these numerical models, we could be able to advise government on a couple, 2 red tide events that have been occurring in Mexico. We also have people studying the sedimentological and stratigraphic characteristics of the Yucatan. Many of you know that we have the reminiscent of meteorite impact that generated a ring, or has the surface expression of this is a ring of cenotes in here, and there is quite a lot of work being done on drills in here to investigate how this happened and how much sediment has been accumulating on top, etc. This is a drawing of the sequence of the rocks found in this course. And that's basically it. Thank you.
Do we have any questions?
Era autopresentación.
Thank you. I was interested in the red tide modeling you mentioned at the end.
Okay.
So do you have operational modeling capability?
No, we don't have. It's like an event based.
Okay.
So because it's not very common that it happens. The last event we had is 2011, and it hasn't happened again. So when the problem comes out, then we take the model out and then do the modeling. But it's not like an operational.
Ismael, for sediment transport, which model are you using?
The model I shown you there is X-Beach, with one of them. The other model is the Cobras model. The detailed model is the Cobras. It's Jose Carlos here. He's Cornell Brown's model. It's a Reynolds average Navier-Stokes.
The list is very interesting on that if you want to collaborate with them.
Yeah, sure.
I can link you. That's what I do.
Our last speaker is from Simvestav, and it's going to present a binational laboratory. Who is our speaker? All right.
Note, I'm not from Simvestav, I'm from UNAM. So Simvestav will not have any responsibility for this talk. So just before we start, just play ourselves in our minds with some thoughts. How we make decisions, how governments can foster government programs in order to have a more sustainable future in a context where uncertainty is irreducible. It's a lot more what we know. It's a lot more uncertainty from our models that our capacity to have any kind of quality decision making. And that is reality today. So that's a problem we are trying to address in this new initiative between two Caribbean countries. And by the two Caribbean countries I'm referring to is the US, United States, and Mexico. They don't always acknowledge that they have a Caribbean, strong Caribbean roots. And about 2 years ago, the two directors of Arizona State University at UNAM, Dr. Michael Crow and Dr. Enrique Graue, launched this initiative, the Binational Laboratory of Sustainability, Vulnerability, and Adaptation to Climate Change, which is called SVAC. So the justification for this binational laboratory is that the region, the Central America, US, Mexico, Central America, and the Caribbean faces and shares serious sustainability challenges. And you can read all of them. And climate change is likely to exacerbate these challenges. So this binational laboratory aimed to enable a tangible improvement in the region capacities for incorporating sustainable development principles in public policies. And that is not an easy task. I have seen in this morning very impressive research and modeling capabilities. But I would also pose that those very impressive capabilities cannot be readily used in decision-making process in governments. So we need an institution that can fill this gap. So the challenge is how we can bring those capabilities into decision-making real time. So that's why we aim to build the capacity for reporting the state of the region in multiple scales, so we can lead to cohesive and informed policy making. So the mission is to be a trusted and committed provider and advisor of information in accordance to the Sustainable Development Agenda. And the goal of the binational lab is to be a node of international collaboration. Now, the problem we're facing is that we have to decide which role we want to play in this very difficult process. And I can see enormous chances, big chances for collaboration between UNAM with INES and the Polytechnical University of Yucatan. I'll try to make this in a stronger case. Well, the thing is that right now you either do leading-edge research and modeling, or you solve problems. You cannot do both. There's no way that you can do both simultaneously. Or you have to be very practical with utilizing models that can be very empirical driven and perhaps naive and very limited, or you devote your time and effort to foster newer models with the leading edge research. So our goal would be to bring these technical and institutional competencies together and create the capacity so we can improve decision-making processes. And in the field that you can locate this kind of work is this called decision-making under deep uncertainty. So how can we can make decisions when we have very little information and the problems are urgent? How can we have high capacity computing facilities providing information for decision makers for taking or deciding on the courses of actions? And I'm not saying only in the decisions that are immediate. For example, how can you plan the investments that the state of Yucatan will require in order to guarantee energy, prevent the effects of coastal erosions, and control urban sprawl, and have an agricultural and fishing development that will be in benefit of the local populations? What decisions the government has to take into account what kind of investments they should produce? And by investments, I'm taking an idea that it will take about 20 years of making them. What will be the future of Yucatan or the Merida for the next 30 years? Can you imagine a city of Merida with 10, 15 million persons for the next 50 years? So those kind of consequences are going to be triggered by the decisions we take now. So, in general, we need better planning tools in the immediate case. And we have this is just an example of marine spatial planning and with spatial modeling. It's a project that we carry out with Semarnat for the North Pacific region of Mexico, just an example. And we can also have capacities for conflict resolution between fishing and loggerhead turtle bycatch, and with the design of reserve for the turtles. So in this case was just a project locating what is the threshold of fishing bycatch that you would also recommend. But on the other hand, it was just a part of the illustration. How can you get to a fair solution for the whole stakeholders? It's not only protecting the loggerhead, but also the fishing communities. And so how could you come up with these kind of solutions? Well, what we need on the one hand is to train scientists, like in this university, like UNAM is trying to do, new professionals. But also we have to broaden up our capacity building scheme in the terms of governments. So our idea is to start creating certifications, accreditations, so people can do a better job in the use of decision-making instruments that we currently have, like environmental impact assessment, like development plans. And on the other hand, we also need to have better decision-making support tools. This is one of the prototypes we're working on, and so that we can bring together stakeholders and come up with solutions. But also, we need these tools to be used by the broader population. For example, organizations of the civil society that would participate in decision-making processes. So this is all my talk. The Binational Lab will have a center of capacity building here in Merida, and we hope to start working with the first accreditation in this kind of tools by the last semester of next year. And also this could be an invitation to collaborate, because we all have, I have seen, as I said, very impressive computing capabilities. And I can see, and it was repeated by the speakers that there was the intention for these tools to help governments and to help the decision-making processes. But let me just make a note of that. This kind of results cannot be used in decision-making process by any government in the world. So the Binational Lab could be a node of collaboration, so we can bring all these capacities together and improve our decision-making capacities for a sustainable future. Thank you.
Do we have any question for our speaker? No? All right. Couple announcements. We are having a break right now, so you have to go to grab a bite or something like that. And for those who are taking the workshop today in the afternoon, it starts at 4 o'clock in Building C, rooms 101 and 102. Okay, and tomorrow our day starts at 8:30 sharp. We're going to have to put some tables here outside this room, so you can register for tomorrow. Okay, so well, that's all for today. Thank you very much. See you for those in the workshop later on.
Take your things and go away. Do nothing, come back again. I'm okay, I'm on my way, my way, my way.